Hey everyone, so in this particular video we're going to look at a new set of approaches that could be useful in synthesis, and these deal with the use of alcohols and increasing or decreasing the length of a carbon chain in an organic molecule. So let's start with this alcohol approach here. So let's say if I have an alcohol and this alcohol here is a more substituted alcohol. Okay, so it is a more substituted alcohol, and what we're trying to do here is convert it into a less substituted alcohol. I'm going to show you two scenarios here, and for the first scenario, let's say that the less substituted alcohol that I want is this alcohol. Now, why am I calling these the more substituted and the less substituted? Because this first alcohol, the starting material, is a tertiary alcohol. It's tertiary in nature, whereas the product is a secondary alcohol. Now, to synthesize a less substituted alcohol, the reaction that we use would be a hydroboration oxidation. But to use this reaction, the first thing that we need to do is actually install a double bond between install a double bond that would include this secondary carbon, or that would involve that secondary carbon where I would like to put that hydroxyl group. So one of the approaches that can be used is to do a dehydration reaction on this tertiary alcohol. So the dehydration can be done using concentrated sulfuric acid and heat. So if I do this reaction, I'll get this alkene product. And by doing this reaction, notice how I've installed a double bond that involves the carbon, the secondary carbon where I would like to put that hydroxyl group or install that hydroxyl group. And so now that I have this double bond or this alkene product, I can finish this off by doing a hydroboration oxidation. So if I react this alkene with borane THF and follow it with the oxidation, okay, again, remember these reactions, the hydroboration and the oxidation, these are done in two steps. So it's a sequential stepwise reaction. So you do the hydroboration and the oxidation. I will get the hydroxyl group on the less substituted alkene. And again, the key was to involve or include to involve that carbon, the secondary carbon, where I wanted to install the hydroxyl group in a double bond, an alkene, so that then I could actually do the hydroboration oxidation and put the hydroxyl group over there. Okay, now this is one of the approaches, but with alcohols, as we will see in the next panel, alcohols, remember, these can be converted into tosylates. So I could do the same reaction by a different approach. So I could react this starting tertiary alcohol with tosyl chloride, okay, and pyridine, so as a base, and this would result in a tosyl ester. So I make the tosylate. And now once I've made the tosylate, recollect that the tosylate behaves pretty much like a halide. It's a good leaving group. So I could do elimination reactions on this tosylate. So an E2 reaction. Okay, I could do an E2 reaction involving this tosylate, so that I put a double bond with that secondary carbon or converting into an alkene. Again, the idea here is to make an alkene where the double bond involves that secondary carbon. Okay, we want to engage this carbon in a double bond. So if I react this tosylate with say sodium ethoxide, which is a strong base, use this in a polar protic solvent, that would give me an alkene. And now from this alkene, I can do the hydroboration oxidation. So the same sequence of events. After this, I react it with borane THF, and secondly do the oxidation. Okay, so that I convert that more substituted alcohol, the tertiary alcohol, into a secondary alcohol, and this time through the intermediacy of a tosylate, and then doing an E2 reaction. The first approach was to do a dehydration and then do a hydroboration oxidation. Now, starting from this tertiary alcohol, okay, that we have, there's another primary alcohol that you could potentially make. Okay, which is this. Now notice how this initial alcohol is tertiary in nature and the product or the target is a primary alcohol. So how would I achieve this goal? Because in this particular case, if I do a dehydration, okay, the dehydration is going to give me the alkene that I got previously or in the previous panel. That would be the major product from a dehydration reaction. And since it does not install a double bond between the carbon where we would like to put the hydroxyl group, okay, on that primary carbon, that is not involved, because this is where we want the hydroxyl, the double bond to form, but that does not happen here. So we could take a longer route, okay, so we'll come back to that, but doing the tosylation route, okay, tosyl chloride with pyridine is advantageous here, because once I convert it into the tosyl ester, realize that behaves very much like a halide, so I could now do an E2 reaction, but I'm going to use a bulky base here. Okay, potassium third butoxide with third butanol, and if I do that, then the product that I get is going to be the less substituted alkene, where the double bond is now formed between the primary carbon and that tertiary carbon. So I'm actually making the double bond where I would like it to be. And now that I have this primary alcohol, what I can do is I can react this primary alcohol with borane, or do a hydroboration oxidation on this primary alcohol to get, not the primary alcohol, I misspoke, on the alkene, the less substituted alkene. I do a hydroboration oxidation on this less substituted alkene to make the primary alcohol that I want. And on the other path where we did a dehydration initially, what I could do is from that alkene, I could do a hydrohalogenation if I wanted to pursue that path or continue along that path. If I do a hydrohalogenation, it will give me an alkyl halide, and that alkyl halide can be converted into this less substituted alkene using a bulky base. So I can merge onto this other pathway and continue to make that alcohol that I want. Okay, so there are possibilities. So again, the point being, there are various approaches. As long as you choose the right reagents and choose the right intermediates, you're going to make the same product. Okay, now let's look at some reactions that actually allow us to change the length of the carbon chain. So for example, I have an alkyne, and what I want to do is I want to convert this alkyne into a longer chain alkyne. We are starting with a terminal alkyne here, and I want to convert it into an internal alkyne. Okay, Now, a good thing or a good characteristic of terminal alkynes is that they can be deprotonated using a strong base such as sodium amide. Okay, because this hydrogen on this terminal alkyne is acidic, so it can be deprotonated. So I can convert that terminal alkyne into what's called an acetylide ion. Okay, you can convert it into an acetylide ion, and now the acetylide ion can behave as a nucleophile. So if I react it with a alkyl halide, I will get the product. Now let's do some carbon count. Let's count our carbons here. So the starting alkyne is 4 carbons. The product is 6 carbons, which means we need to bring in 2 more carbons. So to bring in 2 more carbons, I'm going to react this acetylide with ethyl bromide. Okay, now just to track it again to show you how we're doing it. So we have 1, 2, 3, 4 carbons here, and I'm essentially bringing in 5 and 6. So total 6 carbons. Okay, so this is just an SN2 reaction where the nucleophile attacks and the halogen is kicked out. So I get that internal alkyne. Now imagine a scenario where something similar, where maybe we're actually starting with an alkene. Let's say we have this alkene, and I want to convert this alkene into an acetylide ion. Oh, sorry, not an acetylide ion. I want to convert it into an alkyne. Okay, so we're starting with an alkene, and I want to convert it into an alkyne, but also realize that we are increasing the number of carbon atoms here. So we are bringing in that triple bond when we're doing this synthesis. Okay, so how could I do this? Now, since we have an alkene to start off with, we would need to convert it into an alkyl halide, because going back to the previous example, notice how an acetylide ion can do an SN2 reaction on an alkyl halide to give us an alkyne. So we are going to use that approach, and so essentially I'm going to convert it into an alkyl halide. So I'm going to do a hydrohalogenation, anti-Markovnikov. So I'll use the peroxide effect, and this would convert my alkene into an alkyl halide. And the reason I did this anti-Markovnikov addition is because I want a 3 carbon chain for my product. Okay, I want 3 carbons for my product, so that's why I did this anti-Markov. And then once I've done this, all that's missing as far as the product is concerned is that triple bond, the acetylide. So I can bring that acetylide in as an acetylide ion. So if I react it with sodium acetylide, so this is the simplest alkyne that's possible. Okay, so we have 2 carbons here, and one of these carbons is actually deprotonated, because again, realize there is a hydrogen here. The hydrogen on the other end is deprotonated, and as far as the product is concerned, there is a hydrogen on that end, that carbon number 5. So when we do this reaction, again, this is an SN2, it attacks, the halogen leaves, and it will give us the product. Okay, so we can use the acetylide chemistry to increase the carbon chain length. And now, since we're converting it into alkynes, realize that we can convert the alkyne into an alkene or an alkane, so we can increase carbon chain length that way. Okay, now let's look at an example where we are going to decrease the carbon chain length. We're going to split the molecule. Okay, so let's say we have a molecule where we have a double bond, or it's an alkene, and this is a 6-carbon alkene. So we have 1, 2, 3, 4, 5, and 6. Okay, and what we have to do is, we want to convert this alkene into an aldehyde with 3 carbons. Okay, this is an aldehyde with 3 carbons. 1, 2, 3. And so it looks like what we have to do here is we need to break this alkene in the middle, and we have our product is an aldehyde. Okay, so this is an aldehyde. So if you recollect, one reaction that allows us to convert an alkene into an aldehyde and simultaneously break the molecule, okay, is the ozonolysis reaction. So with this alkene, if I do an ozonolysis on it, react it with ozone at low temperature, and follow it with a quenching, then I will get that aldehyde. Now, yes, it's true, from that alkene, since we're breaking it symmetrically, we will get 2 molecules of that aldehyde, but that stoichiometry may not be given. Okay, you may only be given 1 molecule, but when you break it, you get that molecule, you get 2 of those. That's the thing. Okay, now I want to make some connection here. Notice this alkene that we have on this panel can be synthesized from the alkyne that we had on the previous panel. Okay, this alkyne, 6-carbon alkyne, can be converted into this alkene using hydrogen gas and Lindlar's catalyst. Okay, so there's a connection between your alkynes and the alkenes. Okay, that's important to remember. So that's why once we've done this extension of the carbon chain using the acetylate chemistry, we can convert our terminal alkyne into an alkene. And this alkene here is a cis alkene. So that's why we are using this Lindlar's catalyst, because we want to make the cis alkene. If we wanted to make the trans alkene, we could have done that too. Okay, because if I reacted this terminal alkyne with sodium and ammonia liquid, that will give me the trans alkyne. So 1, 2, 3, 4, 5, and 6 carbon. So it would give me the trans alkene that way. Okay, so we can convert the internal alkyne into a cis alkene or a trans alkene, and then continue on to do reactions. Okay, so those were some additional synthesis approaches that are useful. Now, these are not exhaustive. Okay, I'm just like trying to show you some of the scenarios. When you look through, as you practice, it should be more and more helpful. Okay, bye.